Hello, my people. Let's go ahead and continue on talking about Newton's method. Let's do some examples. Now, this particular function is going to be, let's go ahead and go to our y equals, okay? And let's go ahead and plug it in. We have x minus e to the negative x, or of course 1 over e to the x. It doesn't really matter which one you do. So let's go back and let's graph it. And this is probably not a good window for this, but we can go ahead and see the 0 right there on the far right hand side. I mean, if you want to make it a little bit nicer, we can go -2 to 2 on the x window. Okay, and it looks like it's somewhere around 1/2. So why don't we go ahead and estimate 1/2, okay? So I know that basically my first estimate is going to be 1/2. I need to go ahead and find f prime because it needs to be part of, I need to go ahead and, even if you're doing it in the calculator and you're not actually plugging in f prime, I am going to want to see f prime. I mean, we are doing calculus and not just pushing buttons in the calculator. And when I basically get the f prime, it's 1 plus e to the negative x, because of course the x goes to 1 and the negative right there gets unnegativized by the chain rule, the derivative of the stuff, right? So we know that this, of course, winds up being our y1, this winds up being our y2, and of course we know that our x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And of course that becomes, in terms of our home screen, we need to basically plug in answer minus y1 answer over y2 answer, and then of course just hit enter a bunch of times. So let's go ahead and let's do that, okay? I'm going to move this over a little bit so I can put this under here without it causing a problem with the lights up above. And so I know that like I said, my x sub 1 is 1/2. My x sub 2 is, well, once you've done a couple of these problems, you still have this right here. You don't have to type it out again. What you really have to do is just put 0.5 in and press enter, and then go up and grab this, because it will work for your new answer and your new y1 and y2, and press enter. And so that new one is 0.566310999. Next is your x sub 3 is, actually, I mean, x sub 3 is that number instead of, well, I mean, it is approximate, but you get what I'm saying. 3165. Next, 0.56714329004, and you see that it's getting really close, right? Because basically it's only changing in the 7th decimal place, and you see the fact that this next one is identical to the one above, so it has stopped changing. You have arrived at your answer. That right there is our approximation for the 0 of that particular function. And actually, if you go ahead and go to the graph, and I'm unsure whether your calculator actually uses Newton's method to do this. It wouldn't surprise me if Newton's method was in the programming in order to find this. So I need to calculate a 0, and I go to my left bound, and I go to my right bound, and I press enter, and I get, I mean, you may not be able to see that depending on how big your screen is, but remember, every time that you do some sort of calculation on the graph, it stores it automatically into x, and we see the fact that the x value that has been stored, the 0 that was arrived at by the calculator, is exactly the same as that which we arrived at by Newton's method, okay? So our 0 is approximately, right, 0.5670. That right there is it. Okay. Let's go ahead. I want to, basically this is the graph. It shouldn't surprise you. And of course, just the fact that we got the calculator to approximate it there. Now, let's go ahead and let's do another example. Now, that is not an equation set equal to 0, but it could be, okay? All we have to do, of course, to make it an equation equal to 0, and therefore make it an equation that is asking and answering a question for a function, is to just shove everything over to the same side. And so that's what we're going to do, right? And that, of course, implies that we're asking a question about f of x, x plus 1 minus x squared plus x. Now, let's go ahead and let's plug that in. Okay. So we have that f of x. We have the square root of x plus 1 minus x squared plus x. I'm going to go back to the home screen. Now, we already have the derivative formulated in y2. But let's go ahead and let's find f prime. And we know that f prime is going to treat that like it's x plus 1 to the 1/2. So we get 1/2 x plus 1 to the negative 1/2. Right, minus 2x plus 1. Now, the graph, let's go ahead and show the graph. It shows us 2 zeros. And let me go ahead and change the window. Negative 1 to 3. Okay. Okay. Now we see the fact that it shows us 2 zeros, so we're going to find both of them. The first 0 looks kind of like negative 1/2. The second 0 looks really close to 2, but just on the negative side, on the left side of positive 2. So let's estimate 1.9. Okay. And here's the thing. When you're actually doing these problems, you will wind up estimating differently than your colleague. But if it is sufficiently close, it doesn't matter, because the same thing will happen. After you press enter, 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 it will all go to the same place. So let's go ahead and let's start with x sub 1 is equal to negative 1/2, and let's find out what happens to it. Okay. So let's go back to the main screen, and we'll say negative 0.5, and now we want to go ahead and go up here and grab our formula, since I don't like keystroking any more than you do. So press enter, and we see the fact that x sub 2 is negative 0.4841553301. Enter again. X sub 3 is negative 0.4840283103, and we see the fact that in each successive pressing of the enter button, there are going to be fewer and fewer decimal places that are changing from one answer to the next. In this one, we see the fact that it's 0.283022. It's basically 7 decimal places are staying the same, and it's only changing in the 8th. That means that it's probably going to be this next one that probably doesn't change at all, and I was correct. Okay, and so 48402833022. Once it has stopped changing, that right there is your approximation. And then we go over to the other side, and we find, let's do x sub 1 over here of 1.9. Okay. And we go 1.9, enter, and that just makes sure that the 1.9 is your new answer, right? So this little formula can grind it out, and you get x sub 2 is equal to 1.897182656. Your next one is going to be 1.897179401. Your x sub 4 is equal to 1.897179401, and it has not changed from your x sub 3, and therefore that is your 0. Now, let's say that you didn't estimate it at 1.9. Let's say you estimated it at 2. Like I said, it's still going to go to the same place, right? And so we'll go ahead and do it at 2. Enter, 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 enter. And we see the fact that it winds up going to the same place. Let's say I estimated it at 1.8. And there you go. It winds up being at the same place. So like I said, as long as it is sufficiently close, you're gonna do just fine in terms of finding those actual values. Now, again, this is basically what the graph looks like. And if you use your calculator to find the approximations, and we'll skip that step this time, you wind up getting exactly what we did using Newton's method. Now, let's go ahead and let's go ahead and explore a second use of Newton's method. And if basically we have entered into this by means of a quick example of linear approximation, because they're both approximation methods and they both use tangent lines to find it, the question may pop into your head, okay, well, can I use Newton's method for the same thing that I used linear approximation for? And the answer is yes. So let's say that instead of linear approximation, I wanted to use Newton's method to find the square root of 2. Now, if I use linear approximation, the square root of 2 exists on the square root function where it's still a little bit curvy, right? The numbers haven't gotten large enough for it to start to lay pretty flat or flatter, such that the equation of a tangent line for many, many inputs winds up being indistinguishable from it. It's still at the curvy part, right? It's still at the beginning. So it's probably a good idea to use something else. Now, if we use Newton's method to find root 2, remember we're looking for zeros. So basically we need to sort of back into the function. You ask yourself, okay, what function, instead of using 2 as the input, you use 2 as the square root of 2 as the output, and say what function would have root 2 as a 0. And this one's pretty easy. It's y is equal to x squared minus 2, because the moment you set x squared minus 2 equal to 0 to find the zeros, you either force factor it into x plus root 2 and x minus root 2, or you shove the 2 over to the other side and it's x is equal to plus or minus root 2. So what we're going to do is we're going to go from root 2, we're going to back into y is equal to x squared minus 2, and we're going to use Newton's method to find one of the zeros. Now you only need to find one of the zeros here because, of course, this function is even and there's symmetry, and this 0 over here is simply the negative of that, and you can see that graphically as well as kind of numerically and analytically. So let's go ahead and let's start with our formula. Okay. And we know that x sub n plus 1, so maybe it's better if I have x sub n plus 1 is equal to that. So we need both the function and its derivative. So we have x squared minus 2, and we can go ahead and plug that in here. So we have x squared minus 2. And basically what we do is we plug in, okay, well, we see the fact that the graph looks like this. Okay. Oh, you kind of look at that and you go, oh, that kind of looks like about 1.5 or 3 halves. So let's use 3 halves as our first approximation, as our x sub 1. And if we use 3 halves, then when we plug it into the formula, and of course on the home screen it's going to be a little easier than this because you're just going to be pressing enter over and over and over again. We get 3 halves minus f of 3 halves over f prime of 3 halves, and basically that winds up giving you 1.416, and the 6 is repeated. That is 17/12. You can plug 17/12 in, you're going to get this approximation, and you go again and again, and somewhere between this is x sub 1, x sub 2, x sub 3, and x sub 4. At x sub 4, it has stopped changing to 9 decimal places. And you recognize the fact that that is indeed what we're looking for in terms of our approximation for the square root of 2. And we've used square root of 2 enough times that we should sort of see that. Now, This winds up being superior to linear approximation, not only for those moments like the square root of square root of 2, where if we use linear approximation, it's kind of that curvy portion of the graph that's not going to give us a really, really good approximation. But it also, because it's an iterative process, gets us right down to the best approximation we can find out to however many decimal places. Now, what we're going to do now is another example, one that's a little less straightforward and intuitive. We're going to be finding an approximation for the cube root of 10. So, if we're looking for the cube root of 10, obviously that's not something that you know off the top of your head. But you do know that the cube root of 8 is 2, so it's probably just a little more than 2. But I know that if I'm looking for the cube root of 8, I need to identify a function that is going to give me a cube root of 10 as a 0. And that means f of x is equal to x cubed minus 10. Right? Because that is going to give me the question, x cubed minus 10 is equal to 0, x cubed is equal to 10, and x is equal to the cube root of 10, right? Because that's the process by which we actually analytically evaluate zeros. And so x cubed minus 10, we confirm the fact that that's the function that we want. And now we want its 0. And we know that f prime, this is going to be a pretty easy one, is 3x squared. Now, let's go ahead and go to, again, we're going to go to the y1, and we're going to type in x cubed, be careful to press the right arrow to get it down from the exponent, x cubed minus 10, and let's go ahead and graph. And it basically looks like it goes through just to the right of 2, okay? So let's use 2.1 or 2.2 for our first approximation. How about 2.2? And so, actually I'm going to keep the calculator up here. So if we have x sub 1 is equal to 2.2, I simply need to go again back to the home screen, type in 2.2 such that it becomes the answer for the home screen. And then I simply need to scroll up to find my formula. And my x sub 2 is 2.155371904. And my x sub 3 is equal to 2.154435098. Okay, that changed in the third decimal place. X sub 4 is 2.154443469. And of course that changed in the sixth decimal place. We're getting closer. And x sub 5 is equal to 2.154443469, and that did not change. That is my cube root of 10. And if you want to go back to if you want to basically look for it on the home screen, you can do 10 to the 1/3 power, or you can go to this math screen right here and do the cube root of 10, and that gives us exactly the same thing. Or if you want to go to the graph and calculate the 0, you're going to, again, get exactly the same thing. Okay, go left bound, right bound, press enter, and if you go back to the home screen and press X, which it's been stored into, you get exactly the same thing, and that is your cube root of 10. And like we said, just a little more than 2. Okay. And here, of course, is we saw it on the calculator, but there's a little bit bigger version of the graph. Because basically it's a cubic function, it's the parent function of the cubics having been moved down 10 units. So, alright, that brings us to the end of this second video. In the next video, which will be the third and final of this playlist, we're going to talk about those moments when Newton's method fails. Okay, so, that'll be fun. Bye.